Welcome, cosmic explorers, to another mind-bending deep dive. Tonight, if you happen to find yourself somewhere far from city lights, just look up, you'll probably see it. That hazy, luminous band, almost like a celestial river of light stretching across the vast darkness. We call it the Milky Way. It feels familiar, doesn't it? Ancient, beautiful. But what if we told you that familiar sight is, well, just one part of a much grander, far more mysterious story? What if our galactic home is not only immense and dynamic, but maybe also full of paradoxes that challenge, everything we thought we knew, hinting that maybe our cosmic neighborhood is even stranger than we could possibly imagine?
Indeed. It's really fascinating when you trace how our understanding of this celestial wonder has evolved, from ancient myths all the way to cutting-edge scientific discoveries.
Right.
And each step, it seems, has challenged these preconceived notions, constantly pushing the boundaries of human knowledge. It reveals a universe far more complex than we, ever dared to guess.
Absolutely. So today we're embarking on a truly epic journey. A deep dive into the very galaxy we call home, the Milky Way. And, whether you're completely new to astronomy, maybe looking up at the night sky for the very first time and wondering what that hazy streak actually is, or maybe you're a seasoned stargazer just looking for a fresh perspective on our place in the universe. We'll try to strip away some of the jargon. We're going to bring you the fascinating facts from those ancient kind of enchanting myths right up to the groundbreaking discoveries that are quite literally rewriting our understanding of what makes our galaxy tick.
And our mission today is, to transform your understanding of the Milky Way, to offer you a sort of shortcut to becoming truly well-informed. We want to provide those aha moments, giving you not just the what, but hopefully a profound sense of why it matters, all without getting bogged down in overwhelming detail.
Sounds great.
We'll explore its immense scale, its intricate and often surprising structure, its sometimes violent and dynamic history, and even some scientific paradoxes that still stump us. Paradoxes that might make you question the very nature of galactic stability.
Okay, let's unpack this. Let's start with that luminous band in the sky, the thing we actually see. What is it exactly? And how did humanity even begin to grapple with its existence? Hashtag tag one. What is the Milky Way? The phenomenon and our galactic home. So when you look up at that diffuse, whitish band of light stretching across the night sky, it has this incredibly ethereal, almost dreamlike quality, doesn't it? It doesn't really pinpoint stars. It's more like a soft glow, a kind of cosmic ribbon that just invites wonder. It's truly a breathtaking sight, but in a crucial way, it's also a bit of a cosmic illusion. It's not some distinct external object we're looking at, but rather something we are, inextricably part of.
That's exactly right. And if we connect this to the broader tapestry of human history, the name Milky Way itself, it tells us so much about how ancient civilizations perceived it. It comes from the Latin Via Lactea, which literally means Milky Road or Milky Way, and the Greek Galaxias. Both stem from gola, meaning milk.
Okay.
This common thread across cultures hints at a universal human experience of looking up and seeing this milky, diffuse stream.
And the ancient Greeks, with their rich mythology, they really leaned into that milky imagery, didn't they? We have these incredible, often dramatic myths that tried to explain this celestial phenomenon. One of the most famous tells of the goddess Hera, queen of the gods. Apparently, upon realizing she was unknowingly nursing the infant Heracles, who wasn't her own son, but Zeus's illegitimate child.
Right, awkward.
Yeah. She forcefully pushed him away in a fit of, divine rage. And the milk that sprayed across the heavens, they said, became the shimmering path of the Milky Way. A permanent testament to her fury, I guess.
And there's another equally captivating legend. It describes Rhea, the wife of Cronus. To save her infant son, Zeus, from being devoured by his paranoid father, she famously fed Cronus a stone wrapped in swaddling clothes instead.
Oh, clever.
Very. As she presented this deceptive bundle, milk supposedly spilled from her breast onto the stone, forming that celestial river we know. And these aren't just quaint stories, they are profound attempts to make sense of the cosmos. And they actually gave birth to the very word galaxy itself, meaning Milky Circle. It just reminds us that humanity's curiosity about the universe is, as old as civilization itself.
For centuries, people looked up and truly believed it was some kind of cloud, maybe a celestial vapor. Some even thought maybe a crack in the sky where divine light shone through. But here's where it gets really interesting, where science first started to peel back that ancient veil. In 1610, a rather famous Italian astronomer named Galileo Galilei pointed his newly invented telescope, a marvel of technology back then, at that hazy band. And what he saw for the very first time was absolutely revolutionary. This diffuse light wasn't a cloud at all. It was an enormous number of individual faint stars, just so distant and numerous that they individually remained invisible to the naked eye. It was a groundbreaking revelation that began to truly unravel the mystery, shifting our understanding from myth to, well, the physical reality of the cosmos.
And this revelation leads directly to understanding why we see it as a band across our sky. It's all a consequence of our perspective. See, we are observing from inside a vast, highly flattened collection of stars, our galaxy. Imagine yourself standing in a dense forest. If you look straight up or down, you see a relatively clear patch of sky, right?
Makes sense.
But if you look horizontally, sort of along the plane of the forest, your line of sight passes through countless trees. It appears dense, impenetrable.
So it's exactly like being inside a gigantic thin pancake, right? If you look straight up or down through the thinnest part, you see fewer bits of pancake. But if you look horizontally towards the center or the edge, you're looking through a much thicker layer, so you see far more pancake bits all clustered together. Is that basically what's happening with us and the billions of stars in our galaxy, giving us this illusion of a Milky Band?
That's precisely it. A perfect analogy.
It makes me think, if the universe has a Yelp review, our galaxy's entry would definitely say, great stars, but the photo opportunities are limited from inside.
Exactly. And adding to that visual complexity, the brightness of the Milky Way isn't uniform across the sky. It can appear quite cloudy or patchy in places.
Right, I've noticed that.
And this isn't just an optical illusion, though. It's due to actual denser regions of stars, sometimes simply called star clouds, and also dark nebulae. These are vast, opaque clouds of interstellar dust that absorb starlight, creating areas with an apparent deficit of stars, almost like cosmic smudges on the celestial canvas.
You can actually trace its magnificent path through the constellations, too, can't you?
Yeah.
In the northern hemisphere, it sweeps majestically across familiar star patterns like Aquila, Cygnus, Cassiopeia, and Taurus. If you head south, it embraces constellations like Crux, Scorpius, and Sagittarius. And it's particularly bright and dense when you look towards Sagittarius. Is that significant?
Very significant. That's a key clue for us. That direction happens to be where our galaxy's very dense, shining center lies. So you're looking through an even thicker section of that cosmic pancake, basically.
Okay, so just to clarify for everyone listening, when we talk about the Milky Way with a capital G, we're now shifting gears, right? We're talking about the entire magnificent spiral galaxy in which our Earth and solar system reside. It's not just the band of light, but the whole cosmic city.
Exactly, the whole structure.
And it's a truly massive and complex home. What does it actually look like, this giant pancake we're inside? What are its fundamental characteristics?
Well, one of the most intriguing aspects here is its basic shape, its morphology. It's classified as a barred spiral galaxy. So try to picture a pinwheel, but with a solid bar of stars running across its center, and then these glorious spiral arms unwinding from the ends of that bar.
Okay, I can picture that.
Its stellar disk, which is where most of the visible action happens, extends out to about 16 kiloparsecs. Now, a kiloparsec is about 3,260 light years, so we're talking approximately 50,000 light years in radius.
50,000 light years
Yeah.
radius. That's hard to grasp.
It really is. To give you a sense of scale, a single light year is about 9.46 trillion kilometers, or nearly 6 trillion miles, so 50,000 light years. If light from one side of the disk started traveling towards the other, it would take longer than all of recorded human history just to make the crossing.
Wow.
The overall diameter of the Milky Way is roughly 100,000 light years, and it's surprisingly thin, perhaps only about 1,000 light years thick in most places. Think of it like a giant cosmic CD or maybe a frisbee, but with absolutely immense proportions.
That scale is just mind-boggling. 50,000 light years in radius. So how many stars are we talking about in this cosmic home? How many suns like ours are packed into that immense space?
The estimates vary, but it's home to an astonishing 100 to 400 billion stars. Billion with a B.
Incredible.
And to grasp its sheer scale even further, consider its mass. Our Milky Way weighs in at an astonishing 1 to 2 trillion times the mass of our sun. Trillion. But here's the truly mind-bending part. The vast majority of that cosmic heft comes from something we can't even see. The mysterious dark matter.
Ah, dark matter again.
Yep. It's like realizing your car is mostly made of invisible stuff, or that the weight of an iceberg is almost entirely hidden beneath the surface. And interestingly, in terms of brightness, it's actually quite a luminous galaxy compared to many other spiral galaxies we observe out there.
That's an incredible number of stars, and we're just one tiny speck among them. So where exactly is our little solar system in all of this? Are we, like, special, maybe near the center?
Yeah, far from it. We are definitely not in the center, not even close, really. The solar system is situated about 7.5 to 8.5 kiloparsecs. That's roughly 27,000 to 28,000 light years from the galactic center.
So about halfway out from the center to the edge.
A bit more than halfway, yeah. We reside in a smaller spiral arm called the Orion Arm, often referred to as the local arm or the Orion Spur. It's kind of nestled quite comfortably between the larger Perseus and Sagittarius arms, and this location is actually quite advantageous for us, probably. It keeps us away from the chaotic, high-radiation environment of the galactic core, while still providing a reasonably clear view of much of the galaxy.
That gives you a real sense of just how truly vast our galaxy is and how small our particular corner of it is. And we're definitely moving, right? We're not just sitting still relative to the galactic center.
Oh, absolutely not. We're in constant motion. Our sun, along with the entire solar system, is orbiting the galactic center at a blistering speed of about 220 kilometers per second.
220 kilometers per second.
Per second. To give you some context, that's incredibly fast enough to travel from New York to Los Angeles in about 20 seconds. But the sheer size of the galaxy means it takes us a staggering 240 million years to complete just one full revolution, one galactic year.
240 million years.
Wow.
So the last time we were in this spot.
Dinosaurs were roaming the Earth. The supercontinent Pangaea was just beginning to break apart. It really puts our human history into an astonishing cosmic perspective, doesn't it?
That's an amazing thought, thinking about the dinosaurs having their own galactic year. But it raises a fundamental question for me, and I bet for our listeners too. If we know all this detail about its shape and structure, why have we never actually seen a true photograph of the Milky Way from the outside?
Yeah.
Why can't we get a galactic selfie with all those spiral arms in view?
Yeah, that's a great question, and the challenge is quite fundamental. We're inside it. It's like trying to take a picture of your own house while standing in the living room. You can photograph the walls, the furniture, but you can't get that overall shot showing the whole exterior. For comparison, we only got that full, clear picture of Earth, the famous blue marble shot, when the Apollo 17 astronauts flew far enough away in space to look back in 1972. To get a similar shot of the Milky Way, a spacecraft would need to travel an almost impossible distance from its disk, hundreds of thousands, maybe even millions of light years. That's a journey far, far beyond our current technological capabilities and really beyond anything we can foresee in the near future.
So how do we know what it looks like then? Are all those beautiful images we see in books and online just artists guessing?
Not guessing, no, but rather a sophisticated scientific reconstruction. It's based on mountains of data. Scientists piece together its appearance by meticulously studying the precise locations, distances, and movements of billions of stars. We also observe other similar spiral galaxies out in the universe, using them as sort of analogs, like looking at pictures of similar houses to guess what yours looks like from the outside. And we investigate the Milky Way's internal structure in detail, including mapping gas clouds, tracing spiral arms, and even studying the supermassive black hole at its core. It's like deducing the intricate shape of a gigantic Ferris wheel while you're riding inside it by carefully observing its individual components, their movements, and their relationships to one another. We build detailed computer models based on all this wealth of data, and these models are continuously refined with new observations, especially from amazing cutting-edge missions like the Gaia Space Telescope. So while it's not a direct photograph, it's a very accurate, data-driven portrait of our galactic home.
Okay, so with that incredible conceptual model in mind, let's dive deeper into its grand architecture. If we imagine our galaxy as this cosmic city, it definitely has its distinct districts, right? Each with its own character, age, purpose. It's not just a random scattering of stars. What's truly captivating here is that the Milky Way is made up of several key structural components that define its magnificent form.
That's an excellent way to think about it. You can visualize it like that giant, very thin pancake we mentioned, but maybe with magnificent syrup swirls. Those are the disk and its spiral arm.
Okay, the pancake and swirls.
Then in the very center, there's a slightly thicker, denser pat of butter, which is the central bulge. Often there's an elongated skewer running through it. That's the bar.
And a skewer, got it.
And wrapping all of this up like an enormous, almost invisible, transparent, spherical cloud is what we call the halo. Each part plays a critical role in the galaxy's life and evolution. Hashtag tag 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 2.2, the galactic disk, and its graceful spiral arms.
So let's start with that fundamental pancake, the galactic disk. This is where the vast majority of our galaxy's stars actually live. And it's this flat structure that contains those famous, beautiful spiral arms we often imagine. But it's not just one uniform layer, is it? You mentioned it's more complex.
No, it's far more intricate than just a single layer. The disk itself is, well, layered. Astronomers talk about a thin disk and a thick disk.
Thin and thick disk. Okay.
The thin disk is the primary stellar hub. It's home to younger, more metal-rich stars. Our sun is a prime example of a thin disk star. Now, when we say metal-rich in astronomy, we're not talking about iron and steel like here on Earth. We mean any elements heavier than hydrogen and helium.
Right, the stuff made inside older stars.
Exactly. These heavier elements are forged inside the hearts of stars and then dispersed into space when those stars die, enriching the gas clouds from which new stars form. So newer generations of stars, like those in the thin disk, naturally have more of them. These young, metal-rich stars move on nearly circular orbits within the plane of the disk and constitute about 80% of the galaxy's baryonic mass. That's the ordinary matter we can see and interact with. This region is very active with star formation, bustling with newborn stars and glittering nebulae, and it rotates relatively quickly, around 220 kilometers per second near the sun.
So the thin disk is like the bustling modern downtown of our galactic city, full of young, active stars. What about the thick disk, then? Is that like the older suburbs?
That's a good analogy. The thick disk, by contrast, is composed of older, more metal-poor stars. They are typically 10 to 12 billion years old. These are like the ancient established neighborhoods. It's about an order of magnitude less massive than the thin disk, maybe only 10–20% of the disk's mass. And its stars rotate a bit slower, moving on slightly more elliptical, less perfectly circular orbits that take them further above and below the main plane. The stars here are generally less active in terms of star formation. They represent a much more ancient epoch of the galaxy's life.
Fascinating. And then we have the spirals, those graceful arms swirling through the disk. They aren't like solid, rigid structures, are they? Like painted stripes that never change.
Correct. That's a really critical point. The spiral arms, like the prominent ones we call Scutum Centaurus, Perseus, Norma, and Sagittarius, are not rigid, static features. They are what we call density waves.
Density waves. Okay, what does that mean exactly?
Imagine a persistent traffic jam on a busy highway. Cars slow down as they enter the jam, they clump together, and then eventually they accelerate out of the jam and move on. But the jam itself persists in a specific location, even though the individual cars are constantly changing.
Ah, okay. So the stars and gas aren't stuck in the arm forever.
Exactly. Gas clouds and stars temporarily pile up as they pass through these waves, becoming denser. Gas density is significantly higher in these arms, making them the ideal sites for active star formation. That's why you find so many young, bright, massive stars and glowing molecular clouds concentrated there, making the arms stand out visually like bright highways in the cosmic city. Our sun, as we mentioned, currently resides in a smaller one, the Orion arm, sometimes called the local spur, which is sort of like a smaller side street connecting the bigger arms.
And I've read somewhere that the edges of this magnificent disk aren't perfectly flat either. It's not like a perfectly pristine frisbee, is it?
That's absolutely true. It's another fascinating detail. The outer parts of the disk are actually warped, almost like a slightly rippled vinyl record, or maybe a Pringles potato chip.
A warped frisbee. Why?
This subtle but significant distortion is likely due to gravitational interactions with other galaxies in our cosmic neighborhood, particularly our largest satellite galaxies, the Large and Small Magellanic Clouds. They're close enough that their gravity is constantly tugging at our galactic edges, pulling them slightly out of plane. It's a subtle reminder that even our vast galaxy isn't an isolated island. It's constantly interacting with its environment.
Okay, moving inward now from the grand disk, we come to the very heart of the Milky Way, the central bulge and the bar. The bulge sounds like a really dense, tightly packed region, perhaps the oldest part of our cosmic city.
It is indeed a dense, ancient region, but with some twists. At the very center of the Milky Way is a moderately pronounced bulge. It's a kind of flattened spheroid, approximately 2.2 by 2.9 kiloparsecs in size. Interestingly, it's classified as a pseudobulge, which is a bit of a technical term.
Pseudobulge. What makes it pseudo?
It means it's less like a perfectly round, static ball of old stars, which is what we call a classical bulge seen in some other galaxies. Instead, ours is more like a flattened, spinning mini disk or maybe a peanut shape embedded within the larger galactic disk itself. It rotates quite rapidly. This distinguishes it from those classical bulges, which typically don't spin much. Our bulge mainly contains stars older than 7 billion years, but intriguingly, there are some younger ones mixed in too, and it has a relatively high average metallicity, which was a bit of a surprise.
And it must be hard to study, right? Looking through all that disk material.
Incredibly challenging. There's so much intervening dust and gas along our line of sight to the center, it blocks almost all visible light. However, astronomers found something called Bade's window, which is a small, relatively clear patch in the sky where the dust is much less dense. It gives us a clearer, though still limited, view into the bulge. Mostly, we rely on infrared and radio waves, which can penetrate the dust much better.
And cutting right through this incredibly dense central region is that other structure you mentioned, the bar, almost like a cosmic core sample running through the middle.
Yes, the bar is a really significant fixture with a radius of about 4 kiloparsecs, maybe a bit more. It's essentially a large, elongated, sort of football-shaped distribution of stars stretching across the central region. It's oriented at an angle of roughly 20 degrees to our line of sight from Earth.
How do we know it's there if it's hidden by dust, too?
Well, that orientation is key. It causes an observable asymmetry in the visible star counts and the distribution of gas in the central region when we look at it. That was one of the first big clues. Also, this bar's powerful gravitational potential significantly influences how gas moves near the center, creating anomalous speeds that don't fit a simple circular rotation model. These odd gas movements provide further strong evidence for its presence and extent. There's even some evidence suggesting a smaller secondary bar nestled within the main one, perhaps only about 150 parsecs in radius, potentially linked to a ring of molecular gas near the very center. It suggests a really complex inner dynamic.
So we have this dense, rotating pseudo-bulge, a prominent bar cutting through it. And at the absolute bullseye, the very heart of the galaxy, there's something even more extreme, right? Something that captures the imagination like nothing else.
That's right. At the absolute geometric center of the galaxy, nestled within the bulge and influenced by the bar's gravity, lies a supermassive black hole. It's known as Sagittarius A star, often abbreviated as SGRA.
Supermassive black hole. How massive are we talking?
It boasts an immense mass estimated at 4.3 million times the mass of our sun. That's 4.3 million solar masses, all packed into a region smaller than the orbit of Mercury around our sun.
Wow. That's unbelievable density.
It really is. And the gravitational effects are extreme. Stars near it orbit at incredible speeds. One star, S2 for instance, completes an orbit in just over 15 years, reaching speeds of thousands of kilometers per second as it whips around the black hole. Another star was observed moving at an astonishing 9,000 kilometers per second near its closest approach.
Incredible speeds.
It's a chaotic, extreme environment. And as we mentioned, observing this region directly is extremely challenging due to the intense interstellar dust absorption that blocks visible light. So scientists primarily rely on infrared and radio wavelengths to peer through the obscuring material, much like using special thermal cameras to see through smoke.
Okay, and finally, encompassing all of these spectacular, more visible structures, the disk, the bulge, the bar, is the enigmatic halo. This sounds like the galaxy's invisible embrace, stretching far, far beyond what we can easily see.
It truly is a spherical embrace. Surrounding all the visible components is the stellar halo. It's a vast, nearly spherical subsystem, extending perhaps up to 80 kiloparsecs from the center. That's over 250,000 light years. And individual stars belonging to the halo have been detected even further out, up to an astonishing 320 kiloparsecs away, nearly 1 million light years. That's an immense volume of space.
But it's not densely packed with stars like the disk or bulge, is it? It's more like a sparse, distant collection of stellar outliers, kind of like remote hermits compared to the city dwellers.
That's a good way to put it. While it does contain maybe a few percent of the Milky Way's total stars, adding up to about 1 billion solar masses worth of stars, the stellar halo itself isn't the main story out there. It's primarily significant for something we cannot see, something that makes up the vast majority of the halo's mass, and indeed the galaxy's total mass. Dark matter.
Ah, the great cosmic mystery returns. This raises that important question again. What exactly is dark matter, and why is it so critical to understanding the halo and, well, the entire galaxy?
Its nature remains one of the biggest unsolved mysteries in physics and astronomy, a puzzle that has captivated scientists for decades. We cannot observe it directly. It doesn't seem to emit, absorb, or reflect light, X-rays, radio waves, or any other form of electromagnetic radiation we can detect. It doesn't interact with normal matter in any significant way we can directly measure, except through gravity.
Only through gravity. So how do we know it's there?
Its presence is powerfully and pretty unequivocally inferred from the galaxy's gravitational dynamics, particularly from how stars and gas move way out at the outer edges of the galaxy in the halo region. Remember that flat rotation curve we talked
It's
about?
like the star's moving too fast.
Exactly. That observation demands a huge amount of unseen mass, providing extra gravity. Dark matter forms this massive extended dark halo stretching perhaps 100 to 200 kiloparsecs from the center, maybe even further. While it doesn't contribute significantly to the total mass in the inner galaxy, its density falls off relatively slowly with distance compared to visible matter. This means that dark matter dramatically dominates the outer reaches of the Milky Way. It accounts for the largest share, likely over 80%, maybe even 90% of the galaxy's total mass. Without this invisible gravitational scaffolding or glue, the galaxy would simply fly apart because of its rapid rotation. It's a profound realization. Most of our galaxy, and indeed most galaxies in the universe, are held together primarily by something we can't see or touch. #3. Milky Way's inhabitants and neighbors.
Okay, so we've explored the grand architecture of our galactic home, from its bustling disk to its mysterious dark matter-dominated halo. Now let's talk a bit more about who actually lives here and maybe who our cosmic neighbors are. The Milky Way is teeming with stars, obviously, billions of them, but you mentioned they're not all created equal. They don't all live in the same parts of town, nor do they share the same history, right?
That's right. Historically, astronomers used a simplified but quite powerful categorization for stars, dividing them broadly into population 1 and population 2. This wasn't just about their location in the galaxy, but crucially about their age and their chemical composition.
Population 1 and population 2. And what did that distinction fundamentally mean for how we understood the galaxy's story?
Well, population I stars are defined as relatively young stars, like our own sun. They're characterized by having high metallicity. Remember, that's the astronomy term for containing a higher proportion of elements heavier than hydrogen and helium.
The recycled star stuff.
Exactly. Population I stars typically move in nearly circular orbits within the flat, rotating galactic disk, mainly the thin disk. This population is also associated with active star formation regions, clouds of interstellar gas, and those loose groupings called open star clusters. They are essentially the newer generations of stars, benefiting from the recycled material of their cosmic ancestors. Population 2 stars, on the other hand, are much older and distinctly metal-poor. They have far fewer heavy elements. This is because they formed much earlier in the universe's history, when there simply weren't as many heavy elements available yet. Those elements hadn't been cooked up in sufficient quantities by previous stars.
So they formed from more primordial gas.
Pretty much. These ancient stars tend to move on more elongated, less ordered orbits, often highly inclined to the galactic plane. You find them predominantly within the non-rotating, roughly spherical halo and also in the central bulge. Globular clusters, those ancient, dense balls of stars, are classic examples of population 2 stars.
Okay, so it sounds like Pop I are the relative newcomers, still forming, full of processed material, orbiting neatly in the disk, while Pop 2 are the ancient pioneers, formed when the universe was younger and less chemically enriched, orbiting in a more chaotic, spherical way. It's almost like a cosmic archaeological dig, isn't it? Revealing the galaxy's history through its different generations of stars.
Exactly. That distinction was incredibly useful and still is conceptually for understanding how the galaxy formed and evolved over billions of years. The presence of metals, for instance, is crucial. It's what allows for the formation of rocky planets like Earth and, by extension, maybe the building blocks for life as we know it. So, newer stars with higher metallicity, like Popeye stars, are considered more likely to host planetary systems similar to ours.
But you said this system is maybe a bit outdated now.
Yeah. Well, it's important to note that this system, while foundational, is now seen as largely simplified. Reality is more complex. The correlation between age, chemical composition, metallicity, and orbital motion isn't perfectly sharp. Instead, we now understand there's more of a smoother gradient, a continuum. We've discovered, especially with large surveys like Gaia, that each galactic component, the thin disk, thick disk, halo, and bulge, actually hosts stars of varying ages and metallicities. The lines are blurrier than we first thought. It makes the galaxy's history and stellar evolution far more complex and interesting than a simple binary division. It's a continuous spectrum of stellar ages and compositions, revealing a much more nuanced story of galactic growth, mergers, and evolution. Hashtag 3.2 star clusters and the interstellar canvas.
Right, and beyond these individual stars, classified by population, the Milky Way is also home to these vast groupings of stars, right? From tightly packed ancient collections to more loosely associated stellar nurseries, these clusters must tell us even more about the galaxy's past and present.
Absolutely. They're like different kinds of communities within the larger city. Let's start with globular clusters. These are truly spectacular ancient structures. They are dense, spherical groupings containing hundreds of thousands, sometimes even millions, of old stars, all packed into a region typically 10 to 100 parsecs across. That's roughly 30 to 300 light years.
Millions of stars in such a small space. Wow.
Yeah, they're incredibly dense. We know of about 150 confirmed globular clusters orbiting the Milky Way, but astronomers estimate the total number might be closer to 200, with some hidden behind dust. They're mostly concentrated in the bulge and the halo, acting like ancient sentinels orbiting the main part of the galaxy. Some are found incredibly far out, up to 100 kiloparsecs from the center, and these are truly ancient objects, typically 11 to 13 billion years old, nearly as old as the universe itself. They're generally metal poor, consistent with being population 2 objects. They are cosmic fossils, giving us invaluable insights into the conditions of the early universe.
So these are like the ancient, densely packed retirement communities of the galaxy, full of very old residents. What about the younger, looser groupings, the bustling new neighborhoods?
Those would be the open clusters. They're much less dense, more loosely organized groupings, typically containing dozens to maybe a few thousand younger stars. They're usually much smaller, around 10 parsecs across. You find them primarily within the galactic plane, especially concentrated in the spiral arms, those regions where active star formation is happening right now. Unlike the ancient globular clusters, open clusters are relatively ephemeral. They usually disperse within a few 100 million years as their stars gradually drift apart due to gravitational interactions with each other and with giant molecular clouds. Over 1,200 of these open clusters are known within our galaxy, and they are constantly forming and dissolving, like temporary settlements.
So open clusters are like the temporary bustling towns full of new residents who eventually move on. And then there are even more ephemeral groupings, right? Even less gravitationally bound.
Yes, those are called stellar associations. These are very young, gravitationally very weakly bound groups of stars that all form together from the same giant molecular cloud. They can be quite large, spreading up to 80 parsecs across, but they disperse even more quickly than open clusters, often within just a few million years after their formation. However, during their brief existence, they can contain some of the brightest, most massive stars known, like O and B type stars, which dramatically illuminate their surroundings and inject energy back into the interstellar medium before they explode as supernovae.
And all of these stars and clusters, these individual points of light and dense groupings, are floating in what seems like empty space. But we know it's not truly empty, is it? You mentioned the interstellar medium before. It's not a perfect vacuum out there.
Far, far from it. That seemingly empty space between stars is filled with what we call the interstellar medium, or ISM. Its composition is primarily gas, about 99% of it, predominantly hydrogen and helium, the basic building blocks of the universe left over from the Big Bang. The remaining 1% is made up of tiny solid particles we call interstellar dust.
Only 1% dust. Doesn't sound like much.
It doesn't, but this dust, even though it's a tiny fraction by mass, is actually very important visually and chemically. It's composed of silicates and carbon compounds, like microscopic grains of sand and soot. This dust is what causes interstellar absorption or reddening, which dims and changes the color of distant starlight, making things appear fainter and redder than they really are. It also causes polarization of light, essentially scattering light waves in a particular way. And crucially, it's on the surface of these dust grains that complex molecules can form, seeding the material for future stars and planets.
So it's not just gas and dust floating passively. What else is going on in this seemingly empty space, making it so dynamic?
Well, the ISM also contains a weak but pervasive magnetic field, which threads its way throughout the entire galaxy, influencing the motion of charged particles and gas clouds. And then there are cosmic rays, incredibly high-energy, relativistic charged particles, mostly protons and atomic nuclei, moving at speeds very close to the speed of light, originating from sources like supernovae. What's truly fascinating is how incredibly dynamic and diverse the ISM is. It's extremely heterogeneous, meaning it's clumpy and patchy. Its temperature varies wildly, ranging from less than 100 Kelvin, that's colder than the land at 173 Celsius, in cold, dense molecular clouds where stars are born, up to 1 million Kelvin or more in hot, diffuse gas heated by supernova explosions or stellar winds.
1 million degrees, wow.
Yeah, incredibly hot, but also incredibly tenuous, very low density. And the density also varies wildly, from extremely sparse regions with less than 1 atom per cubic centimeter up to incredibly dense cores of molecular clouds where it can reach 10 billion particles per cubic centimeter or more. This whole environment is constantly being stirred up, interacting with powerful stellar winds blowing off massive stars and the violent shock waves expanding from supernova explosions. This churns the material, recycles elements, and can even trigger new waves of star formation.
And it's within this dynamic medium that we see those beautiful glowing clouds we often call nebulae, right? The ones you see in stunning astronomical images.
Exactly. Those nebulae are just denser or illuminated parts of the ISM. We broadly classify them based on how they shine. Emission nebulae, also known as HII, H2 regions, are clouds of gas, primarily hydrogen, that are being ionized, meaning their electrons are stripped off by the intense ultraviolet radiation from nearby young, hot, massive stars. This ionized gas then glows brightly in specific colors, particularly red from hydrogen alpha emission. These are literally stellar nurseries, often found in the spiral arms, where new stars are actively being born. The Orion Nebula is a famous example.
Okay, so those are star birthplaces. What about other types?
Then there are planetary nebulae. These are entirely different. Despite the somewhat confusing name, they have nothing to do with planets. They are beautiful, often intricate, glowing shells of gas that have been ejected by dying stars of low to intermediate mass, like our sun towards the end of its life. They mark the final, brief, glorious stage before the star's core collapses to become a white dwarf. They often have stunning, symmetrical shapes.
And the most dramatic ones, the remnants of explosions.
Right. Those are supernova remnants. These are the expanding, chaotic shells of gas and debris left behind after a massive star explodes in a spectacular supernova. These remnants are incredibly energetic, often expanding at thousands of kilometers per second initially. They sweep up the surrounding ISM, heating it and enriching it with heavy elements forged in the star and the explosion itself. They often produce powerful synchrotron radiation, which is basically high-energy light generated when super-fast electrons, accelerated by the shockwave, spiral through the strong magnetic fields within the remnant. These are often incredibly powerful sources of radio waves and X-rays, like the Crab Nebula. It's like a cosmic light show born from destruction.
So the Milky Way, with all its billions of stars, vast clouds of gas and dust, diverse clusters, and dramatic nebulae, it isn't just floating alone in the vast cosmic ocean, is it? We have neighbors. We're part of a larger community of galaxies.
Indeed, we do. Our galaxy isn't isolated. It's part of a gravitationally bound collection, a cluster or several dozen galaxies that we call the local group. This group spans a region about 2 megaparsecs across. A megaparsec is 1 million parsecs, so that's roughly 6.5 million light years in diameter. Think of it as our local galactic county, or maybe a small town in the much larger cosmic landscape.
Okay, the local group. Who are the big players in this neighborhood? Are we the biggest fish in this pond, or are there other giants nearby?
The Milky Way and the Andromeda Galaxy, also known as M31, are the two dominant, most massive galaxies in the local group. They are the gravitational anchors of the system. While Andromeda is generally considered slightly larger in terms of its visible stellar disk and probably contains more stars overall, the Milky Way's total mass, when you include its truly massive dark matter halo, is thought to be quite comparable, maybe even slightly larger, according to some recent estimates. It's still an active area of research.
So us and Andromeda are the two big kahunas. Anyone else significant?
The Triangulum Galaxy, M33, is the third largest member. It's a lovely spiral galaxy itself, but significantly smaller, maybe about half the size and mass of the Milky Way or Andromeda. These three spiral galaxies, Milky Way, Andromeda, and Triangulum, contain the vast majority of the luminous mass in the local group. All the other members are much smaller dwarf galaxies, gravitationally bound to either the Milky Way or Andromeda.
And what about closer to home? Our own immediate companions, the satellites directly orbiting us.
Right. The Milky Way isn't alone in its immediate vicinity either. It's the dominant member of what we sometimes call the Milky Way subgroup, and it boasts over 24 known satellite galaxies orbiting it. Think of them as smaller towns or villages gravitationally tethered to our bustling galactic metropolis.
Over 24. Are any of them famous?
The most famous, easily visible as faint cloud-like patches from the southern hemisphere, are the Large and Small Magellanic Clouds, LMC and SMC. These aren't just pretty celestial smudges, they're irregular dwarf galaxies, and they are still actively forming stars at a pretty high rate. This makes them quite different from many of our other satellites. Most of the other satellites are what we call dwarf spheroidal galaxies. These are much fainter, older, quieter systems, often looking like diffuse blobs of stars where star formation largely ceased billions of years ago. Examples include Fornax, Sculptor, and Leo I and the Second. These smaller companions are all gravitationally bound to us, constantly interacting with the Milky Way's gravitational field, subtly shaping our galaxy's outer halo, and, as we'll discuss later, holding clues about our galaxy's formation history and even its future.
All right, so we've journeyed through the incredible structure and diverse inhabitants of the Milky Way. But our galaxy isn't some static painting hanging in the Cosmic Museum. It's a living, breathing, incredibly dynamic system. It's constantly in motion, constantly evolving. And what's fascinating here is that studying its dynamics, how it moves and changes, has led to some of the most profound and, well, frankly puzzling insights in modern astronomy. These insights are challenging our very understanding of how galaxies work.
Absolutely. The first key aspect of its dynamism is its rotation. The Milky Way isn't a solid, rigid body that rotates uniformly like a spinning dinner plate. Instead, it experiences differential rotation. This simply means that different parts rotate at different speeds. For example, as we mentioned, our solar system orbits the galactic center at approximately 220 kilometers per second. Stars closer to the center generally complete an orbit faster than stars further out, just due to the shorter distance they have to travel.
Okay, different parts moving at different speeds. That sounds pretty straightforward, like planets orbiting the sun at different speeds.
Yeah.
But you mentioned paradoxes earlier. Where does the unconventional part come in? Where does this lead us to a major scientific puzzle?
Here's where it gets really interesting and leads directly to that dark matter conclusion we discussed. One of the most profound discoveries in 20th century astronomy was the observed rotation curve of the Milky Way, and indeed, other spiral galaxies. If the visible matter, all the stars, gas, and dust we can see, were the only thing contributing significantly to the galaxy's mass, then according to Keplerian laws of motion, the same laws that govern planetary orbits, stars further from the galactic center should slow down dramatically in their orbital speed. Just like Neptune orbits the sun much more slowly than Mercury does.
Right, gravity gets weaker further out, so things should move slower. Makes sense.
That's what you'd expect, but that's emphatically not what we observe. Instead, when astronomers carefully measured the speeds of stars and gas clouds, especially in the periphery of the galaxy, far from the central bulge, they found that their orbital speeds remain remarkably high, almost constant, or even slightly increasing in some cases. This flat rotation curve, where orbital speeds don't drop off as expected with distance, is one of the strongest and most enduring pieces of evidence for the existence of dark matter. The visible mass alone simply cannot provide enough gravitational pull to keep those outer stars moving so fast, they should just fly off into intergalactic space. The inescapable conclusion is that there must be a huge amount of unseen mass, this dark matter halo exerting the necessary gravitational force. The curve, remarkably, is almost flat or constant in the vicinity of the sun and even further out.
So, just to nail this down, we're saying that the visible stars, especially the ones way out on the edges, are spinning around the galaxy way too fast for the amount of visible stuff, stars, gas, dust, that we can actually see there. It's like spinning pizza dough, and the outer edges are somehow holding together and spinning just as fast as the inner parts, even though they should be flying off according to the amount of dough you see. Therefore, something invisible, this dark matter, must be providing the extra gravitational glue to keep those outer stars orbiting so fast. Is that pretty much the consensus?
That's an excellent way to visualize it. And yes, that is overwhelmingly the consensus explanation within the astronomical community. While alternative theories, like modifications to gravity itself, MOND for example, have been proposed and are still investigated, they generally struggle to explain this observation as elegantly and consistently across the wide range of galactic types and scales as the dark matter hypothesis does. The flat rotation curve is a fundamental cosmic observation that directly points to the overwhelming presence of this mysterious invisible dark matter, making it a non-negotiable component of our models of galactic structure and evolution, even if we still don't know exactly what it is. Precisely. However, here's where things get even trickier. While dark matter helps explain why the rotation curve is flat, that very same flat rotation curve itself presents a major fundamental paradox regarding the stability and longevity of the Milky Way's beautiful spiral arms, those iconic features that define our galaxy's appearance.
Okay, wait. The solution to one problem creates another problem. Let's unpack this, because this sounds like a deeply unsettling issue for our understanding of how galaxies maintain their shape over Billions of years. If stars at different distances are all rotating at roughly the same linear speed, like cars on different lanes of a circular track, all going 60 miles per hour, wouldn't the ones on the inner, shorter tracks complete a lap much faster than the ones on the outer, longer tracks? Wouldn't that cause the spiral arms to get wound up incredibly tightly over time?
You've hit the nail on the head. That's exactly the problem. It creates what's often called the winding problem, or the spiral arm paradox, and it's a truly baffling galactic mystery. Because of differential rotation, especially with that flat rotation curve where outer stars maintain high speeds, the inner parts of a spiral arm should rotate significantly faster in terms of angular speed, completing orbits more quickly, than the outer parts. If we assume the spiral arms are fixed structures made of the same stars and gas over long periods, and we run the clock forward based on the observed rotation, the arms should wind themselves up tighter and tighter, like stirring cream into coffee. Within just a few galactic rotations, a few 100 million years, they should become so tightly coiled that they would essentially disappear, blending into a featureless disk.
A few 100 million years.
Yeah.
But the galaxy is billions of years old.
Exactly, that's the paradox. The spiral structure should be incredibly unstable and short-lived, changing dramatically within just 1 or 2 galactic rotations. Remember, our sun takes about 240 million years for one orbit. This directly contradicts the galaxy's observed age of over 13 billion years, and its clearly maintained, relatively stable, open spiral form that we see now. It raises a deeply puzzling question. Why do the arms appear so well-defined and open precisely in our current epoch if they should have either wound up long ago or be winding up incredibly rapidly right now? It's like finding a perfectly formed whirlpool in a bathtub that somehow hasn't dissipated after hours.
Okay, that is a serious paradox.
Yeah.
If the arms aren't fixed structures made of the same stars, what's the leading explanation? You mentioned density waves before. Does that solve this winding problem?
That's the leading hypothesis, yes. The idea of spiral arms as density waves, proposed by Lin and Xu in the 1960s, attempts to resolve this. In this model, the spiral pattern itself rotates more slowly and rigidly, like a wave pattern moving across the disk, while individual stars and gas clouds pass through the arms. They slow down and bunch up as they enter the denser wave crest, the arm, triggering star formation, and then speed up again as they exit. So the arm isn't made of the same material over time. Just like the traffic jam isn't made of the same cars, the pattern persists, even though the components flow through it.
Okay, so the density wave theory helps explain how the pattern can last longer than the winding time. Does it completely solve the paradox, though? Or are there still issues?
It's the best model we have, and it explains many features, but it's not without its own challengers. For example, what creates and sustains these density waves over billions of years is still debated, maybe interactions with satellite galaxies, maybe instabilities related to the central bar, and some observations still seem difficult to reconcile perfectly with the simplest density wave models. The persistence and origin of the spiral structure remain active areas of research and debate. It's not entirely a closed case.
Fascinating. So the beautiful spirals might be elegant waves, but the exact mechanism is still being worked out. What about more radical ideas? You hinted at something about the rotation curve maybe not always being flat.
Right. There have been some more speculative, perhaps provocative ideas exploring whether our current understanding of the rotation dynamics is the whole story. One line of thought wonders, what if the observed flat rotation curve is just a relatively recent phenomenon in the galaxy's life? What if the dynamics were fundamentally different billions of years ago? Some researchers have explored models with, for example, a time-varying rotation curve. One intriguing, though highly speculative, hypothesis involves modeling the galaxy's rotation backward in time with a hypothetical, non-flat curve that effectively straightens out over billions of years.
Straightens out, meaning the arms were actually straight in the past.
That's the implication of some of these models. If you run the clock backward with such a hypothetical straightening rotation curve, the spiral arms, using, say, the Cygnus arm as a reference point in simulations, might have been nearly straight structures perhaps 3 billion years ago or more.
Straight arms. That sounds like a completely different kind of galaxy. How would that even happen?
Well, this leads to an even more dramatic, speculative origin story. What if, in the very early Milky Way, perhaps triggered by a merger or activity from the central black hole, or maybe even 2 black holes back then, powerful opposing jets of matter were shot out from the center? These collimated jets could have formed the initial foundational straight proto-arms. Then, as the young galaxy rotated over billions of years, these powerful jets would have swept up surrounding gas and stars, gradually slowing down and coiling due to galactic rotation and interactions, eventually spiraling into the magnificent curved shape we observe today.
Wow, jets of creation forming the arms. That is definitely a radical departure from the standard picture. Highly speculative, you said.
Highly speculative, yes. It's an attempt to address the winding problem and the origin of spirals from a different angle, linking it potentially to early galactic activity. It's not mainstream, but it highlights how astronomers are still grappling with these fundamental questions about galactic structure and evolution, and are willing to explore unconventional ideas to resolve persistent paradoxes. It's a testament to how much we still have to learn about our own cosmic backyard.
That's an incredible thought. Our elegant spirals may be originating from ancient straight jets. It really underscores how dynamic and ever-changing our galaxy must be. But how far back does its story go? When did it all begin, and what does the distant future hold for our dynamic galactic home?
Our galaxy's story begins very early in cosmic history. It started forming its first stars around 13 billion years ago, maybe even a bit earlier, not long after the Big Bang itself. The formation seems to have happened in stages. The central bulge, that dense heart we discussed, likely formed relatively rapidly, perhaps in less than 500 million years, experiencing a high burst of intense star formation very early on. This was followed by a slower, more gradual formation of the stars in the halo, probably over the next 1 to 2 billion years, likely from smaller protogalactic clumps merging together. The disk, where most of the action is now and where our sun resides, forms significantly later, perhaps starting around 4 to 5 billion years after the Big Bang. It gradually grew over time as gas cooled and settled into a rotating plane, fueling ongoing star formation that continues even today, especially in the thin disk.
So a busy, chaotic start with lots of rapid star formation in the bulge and halo, but then what? Has it been a constant flurry of activity ever since, like building a city that never sleeps? Or has it had periods of relative calm?
This is actually where it gets particularly fascinating, and it contributes to that later discussion we'll have about whether the Milky Way is typical or not. Evidence suggests that for the past, say, 10 to 12 billion years, the Milky Way has had a relatively quiet life, especially compared to many other large galaxies. It seems to have been free from major catastrophic mergers with other large galaxies during this long period.
Really? A quiet life for 12 billion years? That sounds unusual for a galaxy.
It does seem somewhat unusual. This relatively uneventful recent history, particularly the lack of major mergers, might make our galaxy somewhat atypical compared to many others of similar size, which often show clear signs of more violent and recent collision histories. However, quiet doesn't mean completely uneventful. It certainly experienced smaller mergers with dwarf galaxies. We see the evidence of these encounters today as stellar streams, elongated trails of stars, stripped from disrupted satellite galaxies crisscrossing the halo. Astronomers have identified remnants of several such past mergers, like a significant one with a galaxy nicknamed the Kraken Galaxy about 11 billion years ago, and possibly another major accretion event involving a dwarf galaxy known as Gaia Enceladus, or the Gaia Sausage, which contributed many stars to the inner halo perhaps 8–10 billion years ago. These events left behind these telltale cosmic breadcrumbs tracing our galaxy's assembly history.
So we've had a good, long run of relative peace, punctuated by swallowing a few smaller neighbors. But the universe is a dynamic, ever-changing place, and I imagine that peace won't last forever. What does the cosmic forecast look like for our galactic home? Are there any big events on the horizon?
You're absolutely right, the peace won't last. If we look ahead, cosmic collisions are definitely in our future. First up, in about 2.4 billion years or so, our galaxy is predicted to have a significant collision and begin merging with its largest satellite galaxy, the Large Magellanic Cloud, LMC.
LMC is going to crash into us.
Yes, simulation suggests it's on a collision course. This event will likely have noticeable effects, potentially triggering a burst of star formation, disturbing the galactic disk, impacting the halo structure and metallicity, and possibly even funneling gas towards the center, increasing the mass and activity of our supermassive black hole Sagittarius A. This will be a major event for our local galactic neighborhood.
Okay, so a collision with the LMC in about 2.4 billion years. And then the really big one, right? The ultimate galactic smash-up that astronomers have been predicting for years. The collision with Andromeda.
Indeed. After the LMC merger plays out, a much larger, truly epic event looms on the more distant cosmic horizon. The head-on collision and subsequent merger with the Andromeda Galaxy, M31, our closest large galactic neighbor. Andromeda is currently hurtling towards us at a staggering speed of about 120 kilometers per second, roughly 270,000 miles per hour. Based on its trajectory and speed, this grand slow-motion merger is projected to begin in about 4 billion years.
4 billion years. What will that look like?
It will be a spectacular, drawn-out process. Over the subsequent 2 billion years or so after the initial encounter, the two magnificent spiral galaxies will dance around each other, tidally distorting and stripping stars and gas from each other, before finally fully merging. The end result, maybe 6 billion years from now, will likely be a new, much larger, somewhat chaotic elliptical galaxy, sometimes playfully nicknamed Milkomeda or Andromedway. It's important to remember that while the galaxies themselves will collide, the space between individual stars is so vast that direct collisions between stars are extremely unlikely. However, the gravitational chaos will be immense. Our solar system will almost certainly survive, but it's quite likely we could be flung out to a much greater distance from the new galactic center, experiencing a very different night sky, perhaps even seeing the newly formed giant elliptical galaxy from an entirely new, more distant vantage point. It's a truly grand cosmic ballet with a dramatic finale.
It's truly incredible to think about the Milky Way's possibly violent past, and it's definitely a dramatic future collision with Andromeda. But how did we even get here? How did we get from ancient people seeing a faint Milky Band and telling stories about gods to these mind-boggling scientific models and predictions about galactic mergers and supermassive black holes? This deep dive wouldn't be complete without looking back at the human journey of discovery itself, right? How do we figure all this out? Hashtag tag 5.1, early explorers and conceptual breakthroughs.
Absolutely. That journey of discovery is just as fascinating as the galaxy itself. As we touched upon earlier, the Milky Way, as that visible luminous band in the sky, was a source of profound cultural, religious, and philosophical meaning across countless ancient civilizations. It was a canvas for myths, legends, and spiritual reflection for millennia. But scientific inquiry, the process of moving beyond myth to systematic observation, measurement, and theoretical modeling, really began to take hold much, much later.
And it all started with a pivotal technological leap, didn't it? That seems to be a recurring theme. What was that crucial moment, and who was the key player?
That's right, the invention and astronomical application of the telescope. Galileo Galilei, back in 1610, was the one who famously pointed his newly crafted, albeit small and simple by today's standards, instrument at the sky, specifically at that hazy band. His observation provided the first major scientific breakthrough. He saw unequivocally that the Milky Way was not some nebulous cloud or celestial vapor, but was composed of countless individual stars, just too faint and numerous to be resolved by the unaided human eye. This single observation fundamentally shifted our understanding from a mystical, ethereal phenomenon to a physical collection of distant celestial bodies, profoundly altering humanity's perception of the cosmos and our place within it.
But just knowing it was made of stars didn't automatically tell us its shape or our place within that structure, did it? When did people start to move beyond simply observing the stars within it and begin to actually model its overall structure to figure out what kind of larger entity these billions of stars actually formed?
That crucial conceptual step came much later, really taking shape in the 18th century. Visionary thinkers started proposing models. Thomas Wright, an English astronomer in 1750, published an original theory or new hypothesis of the universe. He proposed early models, suggesting that the stars might be arranged in a vast disk or perhaps a spherical shell. He reasoned that if we were located inside such a flattened structure, looking along the plane of the disk would mean looking through many more stars, thus explaining the appearance of the luminous band across the sky.
Okay, so the disk idea started emerging.
Yes, and building significantly on Wright's ideas, the German philosopher Immanuel Kant in 1755 published his groundbreaking work, Universal Natural History and Theory of the Heavens. Kant argued much more forcefully that the Milky Way was indeed a vast rotating system of stars, likely shaped like a lens or a disk, orbiting a massive central body, though he didn't know what that body was. Even more boldly, Kant went further and speculated that some of the faint, fuzzy patches of light observed in the sky, known then as nebulae, were actually other incredibly distant island universes, other galaxies entirely, just like our own Milky Way, separated by vast voids of space. This was truly revolutionary, almost prophetic thinking, long before astronomers had any observational evidence to confirm it.
Wow, contradicting other galaxies way back in 1755. So these are brilliant theories. When did someone actually try to map it, to put some numbers on it, to quantify its size and shape rather than just theorizing?
That brings us to the great observational astronomer William Herschel, along with his sister Caroline, in the 1780s. Herschel undertook the first truly systematic, quantitative attempt to determine the Milky Way's size and shape. He did this through a laborious process called star gauging. He would point his telescope to different parts of the sky and meticulously count the number of stars visible within the field of view, assuming fainter stars were generally farther away. By doing this in hundreds of different directions, he tried to build up a three-dimensional map of the star system. From his extensive data collected between 1784 and 1785, he concluded that the Milky Way was indeed a flattened, disk-like structure. However, he significantly underestimated its true diameter. His model suggested it was maybe 6,000 light-years across and 1,000 light-years thick, compared to our current estimate of 100,000 light-years or more in diameter. And, crucially, his map mistakenly placed our sun very near the center of this disk. He was limited by only observing the stars he could see, not accounting for things that might be blocking his view.
So a monumental effort for its time and a good confirmation of the disk shape, but still quite a ways off from the true picture, especially regarding the size and our location. What was the next big conceptual leap that helped refine Herschel's initial map and correct those errors?
Yes, his work was foundational, but flawed. Later, in 1847, the Russian astronomer Vasily Struve improved on Herschel's methods and analysis. He estimated the galaxy's size to be at least 4 kiloparsecs, about 13,000 light-years, larger than Herschel's estimate. But more importantly, Struve hypothesized and understood the critical significance of interstellar absorption. He realized that the space between stars wasn't perfectly empty, but contained dust and gas that absorbed and scattered starlight. This cosmic fog, he reasoned, would dim distant stars, making them appear fainter and thus seem farther away, or even rendering very distant stars completely invisible. This absorption effect would make the galaxy appear smaller than it really was, and it would also explain why Herschel and others mistakenly thought the sun was near the center because they simply couldn't see the vast numbers of stars that lay beyond the nearby dust clouds in most directions. Acknowledging and eventually quantifying this interstellar absorption was absolutely crucial for getting the scale right.
Okay, so moving into the 20th century, astronomers are starting to grapple with this interstellar dust and the true scale of our galaxy, and indeed the entire universe. But despite these breakthroughs, the debate about the size and our place in it continued, right? Even with more sophisticated telescopes and photographic plates being used.
Indeed. Even in the early 1900s, prominent astronomers like Hugo Seeliger in Germany and Jacobus Kapteyn in the Netherlands, despite more refined star counts and analyses, still produced models that underestimated the galaxy's true size and persisted in placing the sun relatively close to the center. They knew interstellar absorption was a factor, but they struggled to accurately quantify its effects on light coming from very distant objects across the entire galaxy. Their maps, while more detailed, were essentially still stuck within a localized bubble defined by how far light could travel before being significantly obscured by dust.
Then came a truly monumental breakthrough, led by an American astronomer, that really shifted our perspective and fundamentally changed our understanding of our place in the universe forever, didn't it?
That was Harlow Shapley, working at Mount Wilson Observatory in California around 1917. He made a truly monumental breakthrough by cleverly deciding to study globular clusters. He realized these clusters were distributed roughly spherically around the main band of the Milky Way. He meticulously measured their distances using a special type of pulsating star found within them called Cepheid variables, whose pulsation period is directly related to their true brightness. By comparing their true brightness to their apparent brightness, he could calculate their distances. His analysis showed that these globular clusters formed a vast spherical system centered on a point far, far away from the sun in the direction of Sagittarius. He correctly deduced that this must be the true center of the galaxy, and that the sun was located tens of thousands of light years away from it, out in the galactic suburbs. Although he slightly overestimated the galaxy's overall size, initially suggesting a diameter of maybe 300,000 light-years or 100 kc, his work definitively dethroned the sun from the center of the galaxy and revealed its true, immense scale. It was a cosmic revolution.
Dethroning the sun. And this all famously set the stage for one of the most celebrated scientific showdowns in astronomical history, right?
You're referring to the famous Great Debate of 1920, held at the Smithsonian Museum of Natural History. It pitted Harlow Shapley against Heber Curtis from Lick Observatory. They publicly debated two major points. First, the size of our Milky Way galaxy, Shapley argued for his large scale, Curtis for a smaller one, more like Kapteyn's model. Second, the nature of those fuzzy spiral nebulae. Were they, as Shapley argued, relatively small gas clouds within our own large Milky Way, or were they, as Curtis and Kant before him argued, incredibly distant, independent island universes, entire galaxies in their own right? It was a fascinating debate, and in hindsight, both astronomers were partially correct on different aspects of their arguments. Shapley was right about the large scale of the Milky Way and the Sun's off-center location, while Curtis was ultimately proven right about the nature of the spiral nebulae. It really highlighted the key questions facing astronomy at the time and laid the groundwork for the next huge discovery.
And the final definitive answer to that second question, the one that truly blew open our understanding of the scale of the universe and confirmed Kant's bold idea from centuries earlier, came just a few years later, thanks to another legendary astronomer.
That was Edwin Hubble, also working at Mount Wilson, using the then new and powerful 100-inch Hooker telescope. Between 1924 and 1925, building on the work of Shapley and others on Cepheid variables, Hubble meticulously observed and identified individual Cepheid stars within several of those spiral nebulae, most famously in the Andromeda Nebula, M31. By measuring their pulsation periods and apparent brightness, he was able to calculate their distances just as Shapley had done for globular clusters. His results were unambiguous. Andromeda and other similar nebulae were located millions of light years away, far, far outside the bounds of even Shapley's large Milky Way. He definitively proved that these nebulae were not part of the Milky Way, but were indeed separate galaxies, vast island universes comparable in size to our own. This discovery, announced in 1925, single-handedly expanded the known universe by orders of magnitude, transforming cosmology overnight, and revealing that our Milky Way was just one galaxy among potentially billions scattered throughout the cosmos.
It's just incredible. So, with the galaxy's true scale established, and our place in it, and the universe, more clearly defined, scientists could then turn back to figuring out how our own galaxy actually moved, its internal dynamics.
Precisely. With the better sense of the structure, the next step was understanding the motion. In the 1920s, astronomers Bertil Lindblad in Sweden and Jan Oort in the Netherlands made crucial contributions. They analyzed the observed motions of stars in the solar neighborhood and established that the Milky Way rotates differentially, meaning not like a solid body. Oort, in particular, showed how analyzing stellar velocities could reveal the rotation curve and point towards a central mass concentration, which coincided nicely with the galactic center Shapley had identified using globular clusters. Their work laid the foundation for studying galactic dynamics and eventually led to the discovery of the flat rotation curve and the influence of dark matter.
And then understanding the stars themselves, their different types and histories, added another layer to the picture, right?
Yes. In the 1940s, during wartime blackouts, which provided exceptionally dark skies over Los Angeles, Walter Bade, working at Mount Wilson, was able to resolve individual stars in the central region of the Andromeda Galaxy. He realized there were distinct types of stars. He introduced the concept of population I, younger, metal-rich, typically found in the disk and arms, like the bright blue stars he saw in Andromeda's arms, and population II, older, metal-poor, typically found in the bulge and halo, like the reddish stars he saw dominating Andromeda's central bulge. This classification provided a powerful framework for understanding stellar evolution and how different parts of galaxies formed at different times from gas with different chemical compositions.
And mapping the specific structures, like the arms and the bar, came next.
Right. By the 1950s, using radio astronomy, which could penetrate the dust that blocked visible light, astronomers began mapping the distribution of neutral hydrogen gas, HI, in the disk. This revealed the first clear evidence of large-scale spiral arm sections within our own galaxy. Around the same time, radio astronomers also discovered Sagittarius A, the powerful, compact radio source at the very center of the galaxy, though its nature as a black hole wouldn't be confirmed for decades. The galactic bar, however, proved more elusive. While hinted at earlier, its existence and structure were only definitively confirmed much later, primarily in the 1990s, thanks to large-scale infrared surveys that could finally pierce through the thick dust of the galactic bulge and reveal the elongated distribution of stars within it.
And now, fast forward to the late 20th and especially the 21st century. We're living in this incredible era of space telescopes and vast digital sky surveys. These seem to be revolutionizing our understanding at an unprecedented pace, giving us levels of detail and precision we could only have dreamed of just a few decades ago.
Absolutely. The technological advances have been astounding. The late 20th and 21st centuries have truly opened a fire hose of data about our galaxy. Key milestones include the European Space Agency's Hipparcos satellite, launched in 1989. It provided the first large-scale, high-precision measurements of the positions, astrometry, motions, proper motions, and distances, parallaxes, for over 100,000 stars, significantly improving our map of the solar neighborhood. Then came infrared surveys like the 2-micron all-sky survey, 2MSS, in the late 1990s and early 2000s. By observing in infrared light, which penetrates dust much better than visible light, 2MSS allowed astronomers to map the distribution of stars across the entire sky, including deep into the galactic bulge. This data was crucial for confirming the existence and shape of the galactic bar and even discovering hints of that smaller secondary bar near the center. Large optical surveys like the Sloan Digital Sky Survey, SDSS, starting around 2000, have provided detailed measurements, positions, brightnesses, color, spectra, for hundreds of millions of stars and galaxies. SDSS data has been invaluable for refining the Milky Way's structural parameters and, significantly, for discovering numerous faint stellar streams in the halo, those remnants of past mergers we talked about.
And the current king of cosmic cartography, the one generating truly mind-blowing results right now.
That would undoubtedly be Gaia, another mission from the European Space Agency, launched in 2013 and still actively observing. Gaia is essentially Hipparcos on steroids, but that doesn't even do it justice. Gaia is designed to measure the positions, distances, and motions of stars with truly unprecedented accuracy, roughly 200 times better than Hipparcos for many stars. It has already mapped over 1.8 billion objects in our galaxy. It's providing a precise, three-dimensional map of a huge portion of the Milky Way, tracking not just where the stars are, but how they are moving in 3D space, and providing information about their physical properties like temperature and composition. This incredible torrent of data, released in stages, is continuously revolutionizing virtually every area of galactic astronomy. We're using it to refine the structure of the disk, bar, and halo, to trace the paths of stellar streams back to their disrupted parent galaxies, to study the dynamics of star clusters, to map the distribution of interstellar dust, and even to understand the detailed formation history of different parts of the galaxy. It's like having a perfect, constantly updated 3D GPS map of our galaxy, allowing us to perform galactic archaeology, peeling back layers of cosmic history with astonishing precision. Hashtag tag tag outro.
Wow. So what an absolutely incredible journey we've just taken together on this deep dive. We've really gone from ancient myths of spilled milk literally painting the heavens to Galileo's first glimpse of countless stars, from Kant's bold, almost unbelievable hypotheses of island universes to Hubble's definitive proof that expanded our cosmos beyond imagination. And now we're delving into cutting-edge research using tools like Gaia, revealing subtle structures, complex histories, and even fundamental paradoxes hidden within our very own galactic home.
It's quite a story. We've learned that the Milky Way is this magnificent barred spiral galaxy of truly immense scale, maybe 100,000 light years across or more. It has a complex and dynamic structure. The thin and thick disks where stars like ours live and die, the ancient central bulge, the prominent bar influencing dynamics near the core, and that vast, invisible, but gravitationally dominant dark matter halo dictating its rotation and holding it all together.
Yeah, and we explored its diverse inhabitants, too, the different stellar populations telling tales of age and chemistry, the beautiful ancient globular clusters and younger open clusters, and that vibrant, messy, essential stuff between the stars, the interstellar medium, where new stars are born from the ashes of the old.
And we even looked into its dramatic future, didn't we? Anticipating those grand cosmic collisions, first with the Large Magellanic Cloud relatively soon, and then the ultimate merger with Andromeda billions of years down the line. A future where our current Milky Way might become completely unrecognizable, merging into the giant elliptical galaxy Milkomeda.
It's mind-bending stuff. But just when you think you might have a handle on it all, just when you think you understand the basic rules of how galaxies like ours work, the universe, as always, seems to throw another curveball. You see, for a long time, because it's our home and the galaxy we can study in the most detail, the Milky Way has been our primary laboratory for understanding galaxy formation and evolution in general. We kind of implicitly assumed it was, well, typical, a good, average example of a spiral galaxy. But new, exciting, and maybe slightly unsettling research is starting to seriously challenge that fundamental assumption.
This is where things get really thought-provoking right now, and it could potentially reshape our broader understanding of the universe's grand design, or at least the diversity within it. Recent research, particularly coming from projects like SAGA, that stands for Satellites Around Galactic Analogs, a project specifically designed to compare the satellite systems of galaxies similar to our own, is strongly suggesting our galaxy might actually be something of an exception, maybe even an outlier, not the rule.
An outlier.
Uh.
How so? In what ways might we be unusual?
Well, several ways, potentially. New studies integrating data from surveys like Gaia and Saga indicate that, compared to other spiral galaxies of similar estimated total mass, our Milky Way might have a larger effective radius, meaning its starlight is more spread out than average. But surprisingly, it might have somewhat fewer stars overall, or at least a lower stellar mass for its halo mass, than previously thought or compared to its peers. And its central bulge also appears perhaps less densely packed than in some comparable galaxies.
Huh. So maybe bigger in extent, but a bit more diffuse or less star-heavy for its size compared to others. That's quite a twist on the old picture.
It is, and perhaps even more striking are the findings about our satellite galaxy population. The Milky Way appears to have fewer luminous satellite galaxies than many comparable systems observed by Saga. And perhaps more significantly, its smaller satellites, those dwarf spheroidals we mentioned, seem to have stopped forming stars much earlier in cosmic history than the satellites around other similar parent galaxies. Many Milky Way dwarfs quenched their star formation over 10 billion years ago.
So our small neighbors are unusually old and quiet.
Many of them seem to be yes. This implies our Milky Way might have a potentially unique mix, a population of unusually old, quenched satellites, combined with the relatively recent arrival, within the last billion years or so, of the very active star-forming Magellanic Clouds. This specific combination seems somewhat rare. It suggests that our galaxy's merger history, the way it assembled itself by accreting smaller systems, might have been different, perhaps unusually quiet in recent epochs, or maybe dominated by very early accretion events compared to its peers. This complex and perhaps unique history means that our galaxy, our primary laboratory, might not be the best template for understanding all galaxies of its type.
Wow. Okay, this raises a really important, maybe even slightly unnerving question. If our own galactic home, the place we know best and have used as our main example for decades, turns out to be an outlier, not really a typical example, how might that fundamentally reshape our theories about how galaxies form, grow, and interact across the entire cosmos? How much does that change our understanding of the universe's grand design if our local laboratory turns out to be, well, peculiar?
It's a profound question, and it really highlights the true nature of scientific discovery, doesn't it? It reminds us that even with all the incredible knowledge we've accumulated, the universe always has more surprises in store. It challenges our assumptions and forces us to refine our models. It invites us to keep looking up, to keep gathering data, to keep asking questions, and perhaps to embrace the humbling realization that our cosmic home, far from being just a generic example off the shelf, might be wonderfully, uniquely peculiar. And it makes you wonder, what other fundamental assumptions about galactic evolution, about cosmology, about the very structure of the universe might be overturned as we continue our deep dive into the cosmos, constantly refining our understanding of everything around us?
A truly profound thought to leave us with. The universe, always full of surprises, always challenging us to learn more. Thank you so much for guiding us on this incredible deep dive into the Milky Way.